Hi, I want to talk about Maxwell's contribution to Ampere's law and how it closed the circle of our understanding of electricity and magnetism into the generalized idea of electromagnetism, which is why, despite only adding one piece to four laws, he has credit for sort of all four laws as being part of Maxwell's equations. So the whole idea of Ampere's law is that if you take a look at the circulation of a magnetic field around a current-carrying wire, the circulation is equal to a constant, the permeability of free space, times the current that's enclosed by the loop. And as long as you don't have to deal with capacitors in a circuit, that works pretty well. But let's imagine a situation where we have a circuit that has a capacitor in it, like a simple LC oscillator. Now, if we were to draw an Amperian loop around one of those wires and just choose the simplest surface we can, the circle that's bounded by that Amperian loop, then we would have some current passing through that segment of wire, so the magnetic circulation that we find makes sense. But we don't have to choose the simplest shape. We could deform that shape into this kind of tube worm shape that I've drawn on the board here, and if you take a look, if you run it straight through the center of the capacitor, there aren't any charges. Well, if there aren't any charges, there isn't any current. So how could we have that magnetic circulation when clearly there's a place where there are surfaces that do not obey Ampere's law? Well, the solution to this is the explanation behind the effective current that we see in capacitors. Because, strictly speaking, on any capacitive circuit, there isn't a current moving through the capacitor, but there is the equivalent called a displacement current. And the way that that works is, whenever there's a current and a capacitor, a current must be changing the charge on a capacitor. So if we consider a simple parallel plate capacitor, the charge directly determines the electric field. So if the charge changes, the electric field changes, and Maxwell was thinking with Faraday's work, where if you have a changing magnetic field, you get an electric field. So why not a changing electric field potentially produce magnetic fields? Just like with electromagnetic induction. So what Maxwell did was consider that changing electric field as essentially acting like a displacement current. So the electric flux, if you were to draw a Gaussian surface where one surface was right outside the plate of a capacitor, the other surface passes straight through the center of that capacitor, and then you have two surfaces on the side, the flux that you would get through that Gaussian box would be equal to the electric field inside the capacitor times the area of the Gaussian box that you've drawn. Well, that would have to be equal to the charge on the plate of that capacitor if that plate is completely inside that box, divided by epsilon naught. But that charge is changing. So if I were to take the derivative of that charge, I would have epsilon naught times the derivative of the flux. And the derivative of charge with respect to time is how we defined current. But this is not a current where we're looking at a flux of electrons through something. It's a current where it's a changing charge creating a changing electric flux, which is why we call it a displacement current. So Maxwell's contribution then was to say the magnetic circulation from Ampere's law can be from a real current passing through a Amperian surface times mu naught, but it could also be the result of mu naught times a displacement current that would be passing through that Amperian surface. So in general, for any surface, the magnetic flux, or the magnetic circulation that you see around the perimeter of a surface is equal to mu naught times the current passing through the surface that's enclosed by that path plus mu naught times epsilon naught times the derivative of any electric flux through that Amperian surface with respect to time. Thanks for watching.